In this work, we present a multi-authority control function encryption scheme for quadratic functions. Traditional function encryption is a cryptographic primitive that enables data mining between three types of parties: an authority, data owners providing encrypted data, and clients mining data supplied by data owners. The authority runs a setup algorithm defining a system-wide encryption key, called the master public key, and data owners can use such key to encrypt their data. The authority also distributes so-called function keys to clients, and a client holding a function key for a certain function f can learn f of x from a ciphertext encrypting data x. In short, function encryption ensures that the client learns f of x and nothing more. As such, the authority can decide who can compute a function over encrypted data and which functions can be computed. Yet, the authority has no control on the ciphertexts used to compute that function. A client holding function key for function f can evaluate f over any available ciphertext. In a real-world deployment, function encryption could be used for analyzing sensitive data while preserving privacy. For example, this could be used for genetic testing, where each function key would correspond to certain genetic test, and the authority could control which client can run which test. But the authority cannot prevent a client holding certain function key for a specific genetic test to run this test on any specific data owner ciphertext. In reality, function encryption could be enhanced to do so, but the complexity of the scheme would grow considerably, as the access control logic should be embedded in the function key itself. As we have seen, in traditional function encryption, one can apply a given secret key to any ciphertext. Instead, control function encryption was introduced by Navid and others in ACM CCS 2014 to allow the authority to extend control over the ciphertexts that clients mine. If we stick to the example of genomic tests, now the authority can decide whether a particular client can run a specific test on a specific ciphertext or not. In control function encryption, the key generation algorithm becomes a two-party protocol between the authority and the client, where the client provides both the ciphertext and a function, and the authority uses their master secret key. At the moment of encryption, the owners can choose a certain access policy called lambda that specifies what functions can be computed on the data and who can obtain the result. During key generation, the authority decides, based on this policy lambda, whether the key request is to be granted or not. If so, the client will receive a function key that is only functional on the requested ciphertext. Consequently, in function encryption, the authority becomes a policy evaluation and enforcement point to decide who can evaluate a function, which functions can be evaluated, and which ciphertexts can be used for those evaluations. Of course, data owners must trust the authority in correctly enforcing their policy. Ideally, the key generation should require minimal interaction, for example, being 2 rounds only, one for the client to send the function and the ciphertext, and the other for the authority to reply with the function or with a rejection message. In the mentioned first work about control function encryption, the authors provide two schemes, a very efficient one for linear functions and a general one for arbitrary circuits, which relies on garbled circuits. In our work, we enhance control function encryption as presented by Navid and others in several ways. First, we provide a control function encryption that accounts for multiple authorities. In this way, we can avoid the single point of failure of previous work. In our scenario, there are n authorities, and all of them have to agree on an access control decision to make it effective. Next, we extend the model to allow multiple data owners so that applications that require data from multiple sources, like the genetic tests, could be deployed. Finally, we provide an instantiation that allows the computation of quadratic functions. The tools we use are CCA, public encryption, and linearly homomorphic encryption. Similarly to the previous work, our security definitions are geared towards malicious clients and semi-honest authorities. Note that our model accounts for scenarios where a client colludes with n-1 authorities, or where all the authorities are corrupted but the client is not. We also implement a prototype and evaluate its performance on several experiments. The following diagram provides an overview of our model. There are multiple authorities, and each goes through a setup algorithm to define public and private keys. Also, clients have their own client setup algorithm used to define their own public keys. This is not shown in the slide to keep it simple. Note that client public keys were also implicitly assumed in previous work, since their construction required a secure channel between the data owner and the client. At encryption time, each data owner, who is also a client, encrypts a data item and a policy under a public key that is the union of all authority public keys and their own public key. For evaluation, given a vector of ciphertexts, possibly from multiple data owners, and given a function, a client engages in a key generation protocol with each of the authorities sequentially. Each authority analyzes the request and the policies attached to the ciphertexts, and if all authorities grant the request, the client will obtain a function key. Finally, the client runs the decryption algorithm over the ciphertexts and the function key to obtain the value of the function evaluated over the ciphertexts. In the following, we will show our multi-authority control function encryption instantiations in two steps. First, we show a single authority construction that ensures a technique from Catalano and Fiore to evaluate quadratic functions over ciphertexts encrypted by using a linearly homomorphic encryption scheme. Next, we show how to extend to multiple authorities by means of secret sharing and a distributed threshold version of the linearly homomorphic encryption scheme. Catalano and Fiore proposed a technique for evaluating quadratic functions using linearly homomorphic encryption. The idea is that to encrypt a value x from a certain finite ring, like for example the integers modulo prime, one can sample certain randomness r uniformly from the ring and define the ciphertext as x minus r and a linearly homomorphic encryption of r. Having done this, now everyone can homomorphically compute any quadratic function on x at the cost of getting the result masked by the same function applied on the randomness. More precisely, it is possible to compute a linearly homomorphic encryption of f of x minus f of r under the same public key, even without knowing the secret key. We will now show how to use this technique to build control function encryption. In our control functional encryption construction for a single authority and quadratic functions, ciphertexts consist of two parts, A and B, where A corresponds to x minus r and B to a linearly homomorphic encryption of r under the client's public key. Having these two values, the client could recover x. That is why we add an additional layer of encryption on these two values using a CCA2 secure encryption scheme with the authority's public key. Furthermore, the client is given randomness r in the clear. On a key request, the client sends this ciphertext to the authority, who can remove the CCA2 layer of encryption and compute f of x minus f of r, encrypted under the client's public key of the linearly homomorphic encryption scheme. If the authority decides to grant the request, based on the policy lambda that was also given, the client will receive the encryption of f of x minus f of r as the function key. The client can now recover f of x minus f of r out of it using their secret key, and can then remove f of r because the client knows r, getting f of x as desired. Our multi-authority control function encryption scheme is an extension of the previous single authority scheme. However, a number of technical challenges arise when trying to prevent that a client colludes with up to all but one authority. A key idea of our construction is to secret share the encrypted message. In particular, to encrypt the value x, a data owner picks n fresh bindings, R1 to Rn, uniformly at random. Assume that x is R0. The data owner then gives Rn in the clear to the client and creates a chain of ciphertexts, each of which is intended for a certain authority, and it is CCA2 encrypted with the corresponding authority's public key. The ciphertext associated with authority I contains Ri-1 minus Ri in the clear, and also the encryption of Ri under a linearly homomorphic encryption scheme. Given this information, each authority can create the encryption of f of Ri-1 minus f of Ri. Giving these values to the client, who can then decrypt, aggregate the values, and remove the additional term f of Rn, obtaining f of x as desired. However, this design has a security flaw. For example, if the authority colludes with, if the client colludes with authority 1, they can recover x, since the authority has x minus R1 and also the encryption of R1, but the client can decrypt the encryption of R1, obtaining R1 and consequently x. We fix this flaw by using the notion of distributed threshold linearly homomorphic encryption. Our idea is to use public keys from different authorities in their linearly homomorphic ciphertexts, which can be removed sequentially during key generation. We'll refer to the paper for more details about this. Notice how our construction imposes a specific order on communication with the authorities, and it will be very nice to relax this limitation in future work. What we prove about our construction is that it is secure if at least one party is honest, either the client or one of the authorities. And by security we mean that the data owner's data is protected and only the value of the intended evaluations can be leaked. We have implemented a general library for control function encryption based on our constructions. Our library is written in OCaml and uses a relic toolkit for elliptic curves. We have also designed a simple programming language to describe circuits, which gives users fine-grained control on the way functions are evaluated. For the CCA2 encryption primitive, we choose hybrid encryption that uses AES with 128 bits keys and the Kramer-Shoup public key encryption scheme. For the linearly homomorphic encryption scheme, we implement both Payet and El-Gamal and compare their performance. For our multi-authority scheme, however, because our linearly homomorphic encryption scheme must have the distributed threshold property, our experiments are only based on El-Gamal. Our experiments include the evaluation of a machine learning classifier on encrypted data. In particular, we consider a quadratic classifier that maps encrypted images of the MNIST dataset, represented handwritten digits, into 1 out of 10 groups, 1 per digit. In Table 1, we report the times of encrypting these images with our control function encryption scheme and the times for key generation and decryption of the corresponding quadratic classifiers. We also consider the scenario where both the data and the function to be evaluated are hidden. In this case, we need to sacrifice 1 degree in our computation, and therefore our classifiers are linear and consequently less accurate. The results in this case are reported in Table 2. As we mentioned before, for our multi-authority experiments, we need to base our experiments on El-Gamal, since it is a linearly homomorphic encryption scheme which supports distributed threshold decryption, and we cannot use Payet in this case. As a proof of concept example, we consider a small medical record with data of 30 patients. We encrypt the age and systolic blood pressure of every patient and evaluate simple linear regression on the encrypted data, we report the times in the figure, where the key request is with respect to the 4 classifiers that we need in order to derive the regression line. These are the average age, average blood pressure, the variance of the age variable, and the covariance. As expected, the number of authorities slows down encryption and key request linearly. Finally, Table 3 shows the sizes relative to the implementation of our construction. Entries for plaintext and ciphertexts correspond to the size of encrypting one single integer, whose size is bounded by the underlying ring. Note that encrypting a full MNIST image requires encrypting 784 integers. Also note that the size of multi-authority control function encryption keys is independent of the input length and the underlying function. Well, that was all. Thank you very much for your attention. Bye.